All right, so our first speaker is Dr. Vincent Brown. He is currently the Climate Research Director of CLIP in State University. Dr. Brown is an assistant professor, assistant professor in the Department of Geography and Anthropology at LSU. He holds a PhD in geography from LSU, a master's in geography from the University of Tennessee, and a bachelor's degree in geography from Salisbury University. His research interests include climatology, precipitation, climate change, and statistics. His current research focuses on precipitation extremes, particularly in the Southeast United States.
All right, well, it's great to be here with you guys today. My name is Vincent Brown. As you said, I'm an assistant professor of research in the Department of Geography and Anthropology here at LSU. I also serve as the research director of the Southern Climate Impacts Planning Program. And today, I'm going to talk to you guys a little bit about the work that Skip and I are doing in the climate change, and adaptation around here in the Southeast United States. I just want to give a brief background on what SCIP is. As I said, the Southern Climate Impacts Planning Program. We are a NOAA-funded CAP team, Climate Adaptation Partnerships team. There are 12 such active teams across the nation right now. Ours, we cover Texas, Oklahoma, Arkansas, and Louisiana. We have a unique program because we're a partnership between the University of Oklahoma and LSU, so roughly half our team is at OU and the other half is here at LSU. And what we really do at our core is do stakeholder-driven research related to weather and climate. So all of our work, all of the projects that we do have to be usable by somebody who has to help them either adapt or mitigate or be better as they go forward amidst climate conditions. We have a bunch of themes that are going on at SCIP, and this is just showing what our research is going to be like over the next couple of years. So what I'm about to talk today, it doesn't interest you, I'm sure we have something that you can find interesting. So we have a climate-informed planning, developing governance and collaborative capacity. What I'm going to talk about today is extreme events that change the climate that is led by the very guy who's sitting in front of us right here. And then we also have a climate justice theme that we're going to be focusing on the next couple of years. But again, today we're going to talk about that theme 3. And just by dumb luck, I think Juan Ping must have looked at my slide because I'm also going to be talking about tropical cyclones and extreme rainfall events. And again, that is because that is what our stakeholders that we help are struggling with the most, unfortunately. So again, our research is guided by stakeholder-driven challenges related to climate phenomena. So the first thing we talk about again is changing precipitation characteristics and extreme events. Again, big problem down here. And then also tropical cyclones and their impacts to our stakeholders. So again, this whole talk is stakeholder-driven or stakeholder-focused and how we can potentially help them adapt in the face of a changing climate. So the first big challenge our stakeholders are noticing is changing precipitation characteristics. I think everyone knows that as the climate warms, it's going to change the way that precipitation acts and its characteristics. And I think this figure at the top right does a great job of showing that. So we have 2 stations theoretically here that receive the same amount of precipitation over the course of 1 month. And what we believe is going to happen as the climate warms is that we're going to shift from a station that looks like the bottom here, station B, where the precipitation, as you can see, is more frequent, it's less intense, it's kind of spread randomly across the month. So we're going to transition from precipitation characteristics like that to more like station A, that top station. There's more variability in time between events, but when they do occur, they're more intense, they're heavier, and they present challenges to our stakeholders. So again, we're receiving roughly the same amount of precipitation at those stations, but the way it comes is a lot different. That's sort of the general consensus. And our stakeholders are already struggling with things like this. They're struggling with short duration events. They're struggling with extreme events and variability. Perfect example, a couple of years ago in Baton Rouge, I actually got soaked by this event walking across campus. We got over 4 inches of rain in 2 hours. And again, that wreaks havoc to people in the ag industry or water utilities that we work with. And of course, we have extreme events, the Baton Rouge 2016 event. 1 station reported over 31.39 inches of rain in 48 hours. It's incredible. We also had Hurricane Harvey. So stakeholders of our region are plagued by things like this. Some work that we did a couple years back, we looked at, I'm not going to spare you guys the gory details, we looked at trends in hourly precipitation characteristics across the region. We used first order weather stations. And what we saw, just broadly speaking, is that roughly half the stations that we looked at saw an annual increase in precipitation intensity. And at the same time, a lot of those stations saw a decrease in the average duration of events. So the takeaway there is that what we saw sort of broadly was that events were getting more intense using hourly precipitation data and on a shorter duration. So we took this and we presented it at some various conferences just like this. And the Sewage and Water Board of New Orleans happened to be there. And they saw that I was saying that in New Orleans, rainfall events are getting more intense and of a shorter duration. And that really got them not excited at all, but it kind of piqued their curiosity because they were already experiencing that. So that leads to this first sort of adaptation case study that we're going to talk about that Skip and I are working with the Sewage and Water Board of New Orleans. Just a little bit of background. New Orleans is likely one of the most vulnerable cities to climate change. They have subsidence, sea level rise, plagued by extreme rainfall, and tropical cyclones, landlocked, high rates of poverty. And then the Sewage and Water Board of New Orleans is an entity that works in the city, and they're challenged with dealing with the city's stormwater, drinking water, and wastewater. Now, of importance to us, their stormwater pumps are designed to handle 1 inch of rainfall in 1 hour, and then a ½ inch in subsequent hours. Now, what we're seeing and what they've been noticing, they've been telling us, is that capacity is being tested and exceeded quite frequently. In 2021, that capacity was exceeded 8 times in the city, and in 2020 over 9 times. So after we done some engagement with them, Sewage and Water Board was telling us they're undertaking a once in a generation effort to improve operations of their drainage water, stormwater, and we thought, hey, we could help. So what they did is they came to us and they said, we have questions for you, and we think you can help answer them. And these are the 3 questions they posed to us. One of them was, are there certain areas of the city that are more frequently impacted by heavy rainfall events? As a climatologist, over that small of a spatial scale, we were like, maybe, probably not, but we'll look at it for you. That's one of our questions. Then they asked for more detailed, high resolution reconstructions of historical rainfall events to improve the hydrologic model. I'll show you where we're doing some cool work there. And the last thing is really interesting. They were asking how we could incorporate climate and behavioral data to better improve their long-term planning. So basically, they were just curious about what people in New Orleans think about climate change, what people in New Orleans, what residents in New Orleans are struggling with. So we did a big survey for them to help look at that. And here's some preliminary results from those 3 questions. There's one to your right here. We're using a product called GridRAD, which is a 2-kilometer radar mosaic data set. And we're looking, this is just for June, July, August, but we're drilling down to see if certain pixels over New Orleans, which is right there, if certain DBZ values, decimals relative to me, basically higher DBZ just means more intense precipitation, sort of in the easiest sense. And what we're seeing here is there are some areas over Orleans Parish that are more frequently hit by these high DBZ values. And you can see over Lake Pontchartrain, there's a suppression of events. So that really does fit with what we know about the boundary layer and how storms evolve. But there might be, so preliminarily, taking a look at this, there might be something to what they're saying. There might be certain areas with some unique boundary layer effects that are causing heavy DBZ thunderstorms to sit over certain regions of the city. We also are starting to run storms for them to improve our hydrologic modeling. This is the May 1995 event. Parts of the city got over 20 inches of rain in about a day and a half. So again, we're doing this at 1 kilometer scale, 1 minute, and we're feeding this into their hydrologic models to help them better understand where the rain goes once it hits the ground. All in an effort to improve the way they understand flooding in the city. And the last thing, we just got the results of our qualitative survey back, 414 responses. The Sewage and Water Board actually helped us write questions. They put questions on the survey that they were interested in, such as, what category of tropical cyclone will cause you to leave the city? How much more are you willing to pay for flooding? All of those good things. So we're helping, and we're going to be collaborating with them to help feed that in. And the last thing I'm going to get into is tropical cyclone. Stakeholders in our region really struggle with tropical cyclones, and as you can see here, here's a tweet I saw from San Diego. In 2020, Louisiana spent over 20 days in a 5-day hurricane cone of uncertainty. So we're plagued by these events. And as Juan Ping was talking about earlier, just kind of broadly going forward in a warming world, we're expecting the annual frequency of tropical cyclones to decrease, but those that do form could be more intense. They could rapidly intensify more frequently and produce more precipitation or storm more frequently. We have some really cool installing tropical cyclone work going on. Joe Painter back there doing that effort here. Let's talk about that. But what our stakeholders are saying is they're dealing with frequent tropical cyclones, repetitive events. But what I'm going to focus on in the next 2 slides are earlier tropical cyclone events in the season, the 8 earlier occurrences of tropical cyclones. And why that's a problem perfectly displayed here. This is the water level of the Mississippi River in New Orleans. This dark gray line is sort of the median, and then the dark, well, I guess the darker big line is that actual water volume in 2019. And what happened is in 2019, the Mississippi River was running higher than normal, higher than median, and then Hurricane Barry came. Our stakeholders in New Orleans were terrified because if you get a tropical cyclone that coincides with high early Mississippi River flow, you get overtopping of your levees. So we are really interested in sort of the earlier occurrence of tropical cyclones. So to look at that empirically, using Furtado hurricane database, and we analyze the formation dates of tropical cyclones, main tropical cyclones. And for this, I could talk about the problems with Furtado biases for an hour, but just clear things up. We looked at only tropical cyclones, tropical storm strength or greater, and removed short-lived storms. What you're looking at here on this top left panel is the starting date of the first named storm in each year. So basically, in 1860, what was the date of the first storm? 1900, what was the date of the first storm? And so on, the second, third, fourth, and sixth storm. And what we see is this trend towards earlier storm formation dates. So storms are forming earlier each year through time. And what that's causing is a lengthening of the tropical cyclone season. So that's, again, on your x-axis, you have some time, and this is the season length. So the way we calculated length was as soon as the tropical cyclone formed, it gets its state, and then as soon as the last tropical cyclone dissipates, that's the end. So that length of time in the hurricane season is going up, it's increasing. And we looked at why that was occurring. And what we see is the date of the first storm is getting early and early by about 11 days per 11 days a decade. And the date of the last storm dissipating is increasing by about 5 days. So we're getting this sort of divergence, which is causing a lengthening in the tropical cyclone season. And the adaptation there, and this is what our stakeholders are really interested in, are that potentially expand the definition of hurricane season. Maybe we should be alert earlier because the conditions that are favorable for tropical cyclone development are occurring earlier in the season. Lastly, I just want to give a quick shout out to some cool projects that we got going on. We have Romain Lavard sitting in the back right there. Romain, I didn't get his name wrong, is doing some really cool research on oysters, and we're helping them look at future suitable oyster aquaculture locations in the future. Really cool project. They have a poster. I highly recommend you take a look at that. And then lastly, we have a paper that I believe is in review. I know if it tell me if it is or not. But it talks all about moving from restoration to adaptation. The changes that we're seeing, it's all about the Mississippi River Delta. The changes that we're seeing are happening quite rapidly, and we're seeing that restoration is not taking place fast enough, so we have to adapt. And we have some really cool things that we recommend you do. Anyway, thank you for your time. I hope I respected it. And yeah.
Next speaker is Kelsey. She is currently a senior postdoc in the Biophysical Ocean Model Lab at LSU. She has an interdisciplinary background in marine ecology, policy, and marine protected area assessment with relevance to climate change adaptation.
Hi everyone, good morning. We're switching gears a little bit. Thank you for the introduction. I'm Kelsey. I'm again a senior postdoc here at LSU under our fearless leader, Dr. Cheryl Harrison, who is in the back there. Title of my research here at LSU is towards estimating marine ecosystem impacts of geoengineering. So I'm going to make an assumption that a lot of people here know that the climate is changing. This is a graph here showing sea surface temperature changes toward the end of the century. And we have these different scenarios that climate modelers have developed. The shared socioeconomic pathways are the most recent ones. And they're kind of, these different scenarios are contingent on how much we essentially get our act together in terms of reducing emissions to actually semi-control climate change. So you have these different lines here with a lot of uncertainty relative to kind of business as usual, which is a high emission scenario. We're burning out fuels, we have no global cooperation, we're not doing anything, to something that we refer to as kind of the Green New Deal, where we do get our act together, we keep warming relatively kind of closer to the temperature targets. We do like to emphasize that these best case scenarios do not only require stopping emissions and global cooperation, but we also do need to scrub some of the carbon from our atmosphere with developing technology. And even in our best case scenarios, we still have significant climate change. So we are interested in the marine ecosystem impacts of climate change. So obviously sea surface temperature is a huge driver of what happens in the marine environment, but we have these other ecosystem drivers that we do like to point out. We have changes in pH, which is causing ocean acidification. We have declining oxygen, also really important for marine species, and declining surface nutrients. And you will see that a lot of like these uncertainty levels are just huge, like they're incredibly scenario dependent. But what I do want to point out quickly is that we don't have a lot of uncertainty in the changes in pH. We are seeing a significant ocean acidification, which is causing massive ripple effects in the marine environment. So what does that mean for what like happens in the marine ecosystem? So we have coral bleaching. I'm sure a lot of people in this room have heard about that. So the health of many coral reefs around the world is in jeopardy under even 2 degrees of warming, and that's kind of an optimistic target at this point. We also have sea level rise, so we're drowning wetland habitats and flooding coastal communities. We said we've heard there are 2 speakers that has significant impacts for flooding and many other ripple effects down the chain. We also are seeing larger and more frequent algal blooms, which is not only impacting coastal and fisheries, but it's also affecting us. Like nobody wants to see their beach covered in algae. Did I write this? Okay. We also, very important to our Gulf Coast environment here, our fisheries are being disrupted. Just even recreational all the way up to the big commercial fisheries that impact a lot of livelihoods here in the Gulf and around the world. This is coming up now. And again, we do have more acidic waters that are causing significant amounts of coral bleaching. And not just corals, but other calcifying organisms such as clams and oysters and so on and so forth. And just general habitat suitability. A lot of marine species can't live in, they're being driven out of their homes due to lower oxygen levels and shifting habitats, which is causing these range shifts for a lot of marine species. We're seeing tropical species show up in temperate environments, and essentially the entire marine ecosystem is a little bit in shambles right now, and it's projected to get worse. So what is geoengineering? This is an absolute rabbit hole of a topic, so I'm going to keep it kind of like broad and high level. But there's 2 main flavors of geoengineering, and if all you get away from this talk is that geoengineering is the thing and it's happening, then I feel like I've done my job. So the main one that I think many people probably have heard of is solar radiation management, and a lot of these techniques that fall under like SRM, solar radiation management, sound like they're straight out of a science fiction movie, and a lot of the technology actually doesn't even exist yet. But essentially, how I like to think of solar radiation management is we're developing these tools and technologies to essentially turn the sun down. So limiting solar radiation coming into the Earth's surface. We also have carbon dioxide removal. We're specifically looking at marine carbon dioxide. There is terrestrial methods as well. So we're removing carbon from the atmosphere. We're essentially storing it elsewhere. And what we want to really emphasize throughout this talk is that the research and implementation of geoengineering is moving forward, whether we like it or not. So these people are monetized and they're pressing forward, and we as scientists, climate scientists, ecosystem ecologists, we have to be part of this conversation because it's going to have significant impacts regardless of how much gets implemented. So what are the ecosystem impacts to consider? And basically, we don't know what the ecosystem impacts are. We have very little literature to go on here. So that's why we're really pushing for more collaboration for ecologists and climate scientists. And we do also know that this is extremely scenario dependent. So if you saw those lines from the first few graphs that were the lines merged up depending on the scenario. It's also very specific to the geographic distribution that you're looking at. So there's just a lot of uncertainty surrounding what's going to happen to the ecosystem under geoengineering. And nature is, it never behaves the way you want it to. It's inherently not linear, and it's very complex, and it's very difficult to manage and study and figure out what's going to happen down the line. So just a really quick look at scenario dependency. I do think this is kind of helpful to kind of visualize. So we have this temperature target, and this is one kind of flavor of solar radiation management, SAI for short. So you can see that we're very quickly, this is a business as usual scenario. We're exceeding that temperature target. We're not doing anything to control our emissions. So we're implementing solar radiation management to bring that target down to a baseline. Then we also have this is what's called the overshoot scenario, which is based on the contingent on the fact that we get our act together. So we do a little bit of mitigation, we lower our emissions, we also remove carbon dioxide from the atmosphere, and then we use solar radiation management to kind of just bring it back down a little bit, back down to baseline. We don't rely on it entirely. So what does this system, what is the cost of ecological systems? This business as usual scenario is basically catastrophic. We have changes to the hydrological cycle, we have temperature shifts and extremes, and so on and so forth. This overshoot scenario is much more reasonable and a little bit more of a cushion for ecology. We have a potential reduction in risk to species and ecosystems, but it may not be enough for biodiversity areas, specifically the poles. So how do we model marine ecosystem impacts? So step one, we have these incredible Earth system models that have been just increasing in complexity over the years. So we can essentially hack those Earth system models to drive our ecosystem models. So the ESMs, Earth system models for short, are designed to simulate the carbon cycle. And we can look at what is simulated directly and work our way up the food chain using these Earth system models. So we can simulate marine ecosystems. We can project long-term impacts. We can look at global and regional perspectives, and we can answer all of these questions about the future of fisheries toward the end of the century, changes in biodiversity, ecosystem functioning, seafood supply. So this is just kind of one example of how this works. This is the fisheries model intercomparison project that we're part of. So you can see we start kind of small with the phytoplankton and work our way all the way up to large consumers. So these are mainly global perspectives, and I know that this is a more regional crew, but you can see here, if you want, it's hard to see, but if you zoom into the Gulf of Mexico, red is bad, and we see a very significant decrease in fisheries abundance towards the end of the century on the coastline of the Gulf of Mexico, which is where a lot of our really important fisheries are. So I'm going to quickly go through this because I see that I'm maybe running out of time here. Essentially, for the fishery models findings so far, again, these are global perspective, but all I really want you to take away from this graph right here is there's something called trophic amplification. So what that means is as our climate warms, the bigger the organism, you're going to see more impact. So that's our whales, our dolphins, our really important fisheries. We see massive declines in biomass and abundance through all the way through down to this RCP 8.5. That's our business as usual scenario. So that's kind of catastrophic for fisheries. And this was a really incredible figure just because of the model agreement in this figure. But you see here that there's a 5% decline in fisheries biomass for every 1 degree Celsius of warming. And that's kind of striking, that model agreement right there. There was a lot of fisheries models that went into this figure. So to have them all kind of really tight and just really in agreement in terms of their biomass declines was actually really amazing. So we're saying, okay, can we implement geoengineering? Can we work our way back up this catastrophic decline? Maybe, who knows? We still have a lot of unanswered questions. Okay, so what we want to do, a lot of the SRM research has focused so far on this global perspective. We want to bring our perspective down to a more regional basis. So I have a background in marine protected area management evaluation. So I am very interested in working with the U.S. National Marine Sanctuary Service and as well as fisheries closures to look at our sanctuary response to geoengineering. These are what we have identified as very important for fisheries habitat. So we can look at our marine ecosystem models using the solar radiation management existing simulations, and then we can overlay these national marine sanctuaries. So this is the Flower Garden Banks. Maybe people are familiar with that. It's right off here in the Gulf of Mexico. Really, really important to deep sea coral habitat. So can we assess sanctuary design and effectiveness through a climate intervention lens? And it's not just the Flower Garden Banks. The United States has many national marine sanctuaries that are crucial for marine ecosystem biodiversity. But the Flower Garden Banks obviously is one that's close to home and one I'm very interested in looking at. And I think that's it. Thank you so much. Please email me if you have any further questions.
All right, our next speaker is Dr. Vincent Furtado. And Dr. Furtado is an associate professor in the School of Meteorology and also a CASC and Berlin Library residential professor at University of Oklahoma. His research focuses on large-scale climate dynamics, including coupled systems across multiple scales and its applications to seasonal forecasts, predictions of extreme weather, and climate change. Prior to working on the faculty at the University of Oklahoma, Dr. Furtado was a climate scientist and subseasonal weather forecaster for Atmospheric and Environmental Research, which is a private sector company in the Boston area. He has contributed to numerous media stories about weather and climate and his own research, including outlets like the Washington Post, CNN, and Discovery Canada. Outside work, Dr. Furtado enjoys traveling, playing in the National Trivia League, and volunteering with the schools nationwide to encourage education and participation in STEM in the classroom. Dr. Furtado is going to be talking about climate change and extreme weather in the South Central USA.
All right, we'll try to go through this. Thanks for having me. So I want to talk a little bit about some observed climate change, or excuse me, extreme weather trends that have happened across the South Central US to give us a little bit of context. So first, I think it's important, what is extreme weather? Because we use this term all the time, right? And I think we have some perceptions of it depending on what applications we have. So first would be sort of a mathematical definition, right? We think about this distribution of whatever your favorite variable is, rainfall, temperature, wind speed, etc. And then we think about sort of the tails of those distributions as being sort of quote unquote extreme, 95th, 99th percentile, lowest percentile, etc. Right? But actually, there's multiple other kinds of definitions. There might be a bit more what I call impact-based definition. So this might not meet our mathematical definition, but it could be something that could happen that would be extremely impactful for an event or a population. So for example, I have some images here on what we would call extreme weather, flooding in China, wildfires, and extreme cold. And, you know, when we talk to the project, I'll highlight a little bit, when we talk to stakeholders about what is, we actually ask them, what is extreme rainfall? Many of them didn't give us the left definition. They gave us the right definition. It wasn't to them whether or not it rained a certain X amount of inches in so many Y hours. It was whether or not the population was deeply affected by it. So I think this is an important concept that we have to think about when we're talking about extreme weather. As a scientist, I'll focus a little bit more on the left side of this, but I think it's important to keep that in mind. So we've heard a lot about some of the trends in extreme precipitation this morning and things like that. I actually will talk very briefly about that, but I want to highlight the first thing. How about temperature, right? When we think about climate change, the first thing that comes to mind to people is temperature. And so here I have from the latest IPCC report on the left, annual trends in annual hottest temperature, middle is annual coldest temperature, and here is the number of the days exceeding the 90th percentile. And on this graph, we're starting to move towards this other area we heard about. The X's here are actually places that are not safe, where the trends are not safe. Okay? So if we look especially here into the central southern US, you can see on the left-hand side that actually the annual hottest temperatures over this period of 1959 to 2018, there's actually a slight blue hue on there, meaning that they actually come down a little bit. And the trend is not significant, but it's actually negative, which might be counterintuitive. But on the middle panel, so we're almost everywhere across the globe, except parts of tropical Africa, you can see that minimum temperatures are up. And this is important because heat is the #1 killer in terms of extreme weather. And it's not just the maximum temperature, but the minimum temperatures. And so when we went, for example, years ago, I attended a heat workshop in El Paso, and the emergency doctors were there. And they said, actually, it's not the maximum temperature that drives the number of admissions for heat exhaustion. It's actually when the room temperature doesn't drop below 84 or 85. That's their cutoff. So this is a really important trend that's happening here, and you can see across most of the United States and North America, it's all very positive. The number of days exceeding the 90th percentile, again, you look at this map and it should look like everywhere. But again, we have this area here in the southeastern US that has not had a significant trend. Okay, so that's heat. What do we think about? How about cold? So a few years ago, or excuse me, in 2020, we started this project in Oklahoma looking at solving wicked problems and how extreme weather and how we can interact with our infrastructure and a lot of other stakeholders to talk about solving sort of this interaction between extreme weather events and how they're impacting the public. And so one of the things, of course, we were looking about heat waves, drought, and everything. So when the project came out, I said, well, I want to look at cold. And I got a few weird looks at I want to look at cold weather. This is the climate sheet, right? But actually what's been happening is actually, if you look at the panel here, this is the frequency of cold air outbreaks across the central and southern plains of the United States. And you can see that, yes, it was much colder or much more frequent events during the 1960s, 1970s, but after the 1990s, we started seeing an increase in that. The left panel here is actually showing you just what is the typical atmospheric circulation pattern that accompanies these cold air outbreaks. And for reference here, you can see Alaska, that big red area, meaning higher pressure than normal there, and then the blue over the central and southern United States, the big trough. That's our characteristic pattern to get these cold air outbreaks. When we look at the panel on the right panel is showing you the trend over the last 40 to 50 years in that mid-tropospheric circulation. And you can see that it's mirroring what that favorable pattern is, where you're getting much higher heights across Alaska and across the Arctic, which is warming rapidly, and the trend towards lower heights across the Great Lakes and Central United States. So the trend that we're actually seeing is actually favoring more of these polar outbreaks. And I don't think I have to remind people about things like February 2021, which was an extreme event. We also went back in time. Again, this is all work that we recently just published. And we looked at the top, this is the top 37 cold air outbreaks since 1950 across the central and southern United States. And at the very end here, you can see that the February 2021 event was actually the second most severe cold air outbreak that occurred. Number one being that event in December of 1983, which used to be sort of the threshold and sort of this is not bad as it gets. And then 2021 kind of came along and said, well, actually, we need to do a little bit worse. But again, in terms of total severity, we're not seeing a reduction in severity. Maybe see a reduction with time in the future in magnitude, but the severity is really still quite high. And I think this is very important to highlight for people. I won't spend time on this since our speakers this morning talked a lot about trends in extreme precipitation, but what I will talk about is in the project that we're doing, where we're looking at trends in what I call rainy periods, which are 14, 30, and 60-day periods. So these are periods of extreme rainfall, but extending out not just one day, but several days. And so here's a study from my PhD student, Ty Vincent, and what we did was we looked at these 14-day trends of extreme precipitation that's exceeding the 99th percentile. The red is where the trend is going up, the blue is where they're going down, the black line is where there's significance. This was done with quantile regression for those of you that are interested. And you can see across part of the south central US, there is quite a bit of rain going on. There are some areas that have significantly more of these 14-day rainy, extreme rainy periods. The Northeast certainly pops out a lot on this. How about drought? That's on the mind of a lot of people. I think over 80% of the United States currently has some form of drought, and across the south central US and the western, well, the western US has been dealing with it for well over a decade, but the south central US, Oklahoma and Texas, it's gotten really bad this year. And so the left-hand panel is something I pulled down from using some data from NOAA and USGS, looking at trends in the drought and moisture surplus, which is used by the US Forest Service to look at drought. And these are trends since 1980. The brown are declining trends, and you can see certainly across New Mexico and Texas and Oklahoma, we've had a declining trend in that. Declining trend in that, meaning actually increased chances or increased trends in drought. The right-hand side is by Jordan Christian et al. At OU, looking at flash droughts, which we talked about yesterday a little bit, and actually their spatial coverage is increasing across the central and southern United States this time. So these flash drought events are also becoming much more frequent. So the last thing I want to talk about is how does climate change play into this? Because I think it's important not just to recognize the trend, but then understand what the physical mechanisms and processes are, so that we can then explain them to our stakeholders and all those people to make sure they have a fundamental understanding of it. And so I'm just going to highlight 3 mechanisms here. One, the first one is what I call the Clapeyron effect, which basically is as it gets warmer, the atmosphere can hold more moisture, right? In fact, for every degree Celsius, we can hold 7% more water vapor, which of course then can get translated not to extreme rainfall, but also to extreme droughts, because the atmosphere is capable, the evaporative fluxes, there's more that can go into it, right? The next is that there's more instability because of a warmer surface, also going to lead to more intense weather. We saw that with things like the tropical cyclones this morning, but even extratropical cyclones are getting stronger. And this is because of the growing instability that's happening. The last one is work that I've been working on a lot, which is this idea that the jet stream is becoming much more variable and what some would call weightier. So jet stream is that river air in the upper troposphere that usually in the mid-latitudes flows from west to east, but there's undulations that can happen in that. That's what gives us our storms, that's what can give our heat waves, or the new popular term heat dome, right? But that is controlled fundamentally for order by the temperature difference between higher and lower latitudes. And as I showed you earlier, the Arctic is getting warmer. In fact, it's warming twice as much. The rate is warming twice as fast as lower latitudes. So that difference is changing. And that's what's going to cause their jet stream to get weightier. And when that happens, think about that as you get more of these waves, the patterns get much more stationary over time, or in the atmospheric community, we call it block. And so you will start getting these big ridges that are happening, like what happened in the Pacific Northwest last year, like what happened this year across parts of the South Central US and Europe. But also there's the other side. These things have to be bookended on either side by troughs or the low pressure regions, and that's the reason where storminess is going to happen. Okay, so this is an important feature that we have to want, and one that we have to, again, try to understand how is the jet stream changing, how is the blocking patterns changing, and what does that mean in terms of temperature and precipitation and in terms of other extreme weather in our particular region. So I will end it there, and then we'll go to the question afterwards. Thank you.
Thank you. Thank you. You can hold it, you can sit with us here, so we're gonna go into the question and answers. Part. Mr. Brown, Dr. Roberts. Here.
All right, this is, I'm sorry to start a question this way. This is less of a question, more of a request. Not all of us are atmospheric scientists, and we don't know all the acronyms that y'all are using. And it's gonna be incredibly frustrating. So if you have acronyms, if you could like at least just explain what those are, that would be fantastic. And I think we would understand the rest of us a lot better.
Thank you. I have 2 questions. First question is asking for Jason. I know we are following you far away.
Right across the parking lot.
Yeah. So my first question is, as ecologists, we always look at the temperature as both sides, on the high side and the low side. So we all have physiological reasons why the low temperature is important. So I'm very glad to see you talk about this cold temperature dynamics. The question I have is, when you make your calculation based on December, January, and February, what's the threshold you define as your index? So that index is based on kind of physiology or plants or animals. Can we include that variable into the system and maybe directly linked with our product?
Yeah, so the study that I showed there, the variable that we used to define cold air outbreaks was we defined using 2-meter temperature, using the bottom like 10 percentile. So these would be the mean temperature of the day, so a daily mean temperature below the 10th percentile, and it has to be for at least 4 or 5 consecutive days. And that's how we define something called cold air outbreak. Okay, so we do it based on just 2 meter temperature averages. That's how we've defined it there.
Okay, great. We can be talk about more. Say, sure. For this other degree, like in 0 degree temperature.
Sure.
Not like a frequency based on local scale. The second question is for Vincent, and because of COVID-19, I cannot do much international traveling. I started to travel a lot in the US, particularly in some lower Mississippi River. Are interested in 2 areas. One is the agricultural system. They are all like wetland systems. So when you talk about this hurricane or this rainfall events, to what degree those change of vegetation or extreme events affect the agriculture or wetland in Louisiana and the Mississippi and the Arkansas Delta region?
Yeah, so I can extend that. So a lot of the majority of the water that you see in the Mississippi River isn't from, from farther north. And what's going on there greatly impacts what ends up happening downstream. And right now, the river is obviously very, very low. It's a reflection of drought conditions in the northern interior of the United States. From what we're seeing with rainfall, particularly in Louisiana, extreme events have been impacting agriculture. Some groups love it, and other groups that we have hate it. For example, the sugar cane farmers are happy right now that it's been dry, they can go to the fields and harvest the sugar, whereas other folks born in rice are very unhappy because they need the water held in the from the rainfall events. And so what was the second part of the wetlands? So I don't do much work with wetlands. We collaborate with folks over in this department on that. So I can't speak to extreme rainfall in the wetlands, but I know there's a quite a large volume of work going on with some of our partners that are doing that in better
I'm gonna actually jump online real quick to our online participants, because there's a question there, and then we'll come back to the room.
Yes, so we have a comment from Sharon Housen, who's with the CASC, and she kind of echoed what Kate was saying, that it would be particularly helpful to know what those acronyms in the legends of the graphs mean. And then in addition, we have John Nielsen Gammon. He's from Texas A&M, and he's kind of responding to an earlier question about climate change trends.
Yeah, thank you. Yeah, the question, can you hear me?
Yes, we can hear you.
Okay, thanks. Yeah, the question on probable maximum floods. I wanted to make a few comments on that in addition to what Han Ping said. Of course, it's hard to look at trends in probable maximum precipitation or probable maximum floods because these are presumably things that don't happen or are upper limits of what can happen. But we can look at what sort of detection and attribution studies have done on events that approach that level. The closest one being, I think, Hurricane Harvey. And the best study, I think, on that one looked at both observations and models and said that climate change had a 15% increase in the amount of rainfall from Harvey in terms of 3-day point totals. So that probably translates into a 10% or so increase between what the current assessment is of PMP, probable maximum precipitation, and what climate change has done so far to elevate it. Secondly, in a study that I contributed to, we also looked at the role of soil moisture on the flooding in Harvey, the inflows to the reservoirs there. And if you take away a 10-inch rain event that happened earlier in the month, you only affect the inflows by about 6%. So it looks like the increase in intensity of rainfall at PMP levels is winning out over the decrease in soil moisture that climate change might be contributing to. And last comment, this whole issue is going to be looked at by the National Academy of Sciences. They're assembling a committee right now to evaluate ways of factoring in climate change on probable maximum precipitation. Thanks.
Thank you, John.
Do any of our panelists want to respond to any of those comments?
Hi, John. No, those are great comments. I agreed with everything said. John did some really good work on Hurricane Harvey, a great poster about some of the biases in the accumulated rainfall with Harvey and some of the stations. We're actually working on a paper trying to reconstruct the Hurricane Harvey rainfall for use of PAD depth area durations, and we're going to on that. So yeah, I agreed with everything said. Thank you for that comment, John. Can't wait to see the hurricane stall paper as well.
I'll just make one very brief comment. These trends in tropical cyclones, and especially the rainfall from them, are also in some studies are being tied to weaker upper level flow, allowing systems to stall more. So this is also linked to that idea about sort of jet stream winds flowing and things like that. So we've been seeing a lot of these storms that are sort of stalling or not moving as quickly as we once thought. And that does two things. If it's over the ocean, they can intensify more rapidly. Number two is if they stall over land like a Harvey, they can produce, catastrophic rainfall. So also something to consider.
So I was curious, it seems like in this presentation on geoengineering and how climate change is affecting marine species. And in my crude understanding of ecology, I guess I'm familiar with there being two metrics at least of in ecology that are common, species richness and species abundance. And I can see how obviously climate change is affecting both of those metrics, but I'm curious, especially at the higher trophic levels, it seems like richness would be maybe more sensitive to climate change, like you were talking about with like larger organisms, for example. And so I'm just wondering if there's any concern that maybe geoengineering can positively affect maybe something like species abundance, but would be less successful for something like species richness. And if that's a concern that's never discussed.
That is a great concern. I love that question. Mainly what we have, it's all speculation at this point, right? And that is absolutely an important research question. That now, thank you. Now that you mentioned it, I think I had explored something out of my brain, but we're working on a perspectives article that's going to kind of outline some important questions and some research pathways, and I'm definitely going to incorporate that now. So thank you so much. But we do want to highlight, and maybe I failed to do that in the presentation, that geoengineering will have benefits associated with it. That's why we're going to see benefits, and we're going to see risks. We're going to see this positive net gain in richness or abundance and a negative in other areas. And I think it's going to be so spatially dependent, and that has all kinds of consequences, and it completely depends on where you are in the world as what is actually going to happen to the ecological system, what the response is going to be. And once we actually do start running these models, it's going to be very interesting to see how that kind of plays out in different latitudes and different areas of the world. But yeah, that's an absolute very important concern, and that has repercussions for fisheries and for the socioeconomic livelihoods and all the way up and down the line. So thank you very much for that comment. I appreciate it.
Hi, my name is Roman. Vincent mentioned my name. I have a poster. We're doing some work on the oysters and how climate change impacts the fisheries along the coast of Texas and Louisiana mostly. My question is more about, so we heard about effects on land of climate change effects in the marine environment. Really appreciate, I think, this perspective too. What is the current situation about what's in between the coastal environment? We had a question about the wetlands. I know that models can be good, inland, can be good offshore, but what about the zone in between? What is the current status on that? Curious.
I have a comment on that, and I think Cheryl is very happy that you mentioned that question. Because she has been very vocal in making sure that people don't overestimate and don't we need to have that line, like the models cannot very well resolve those coastal processes. And she's very interested in upwelling systems, and we're making all of these conclusions, and we're drawing all of these, we're basically saying all these things, and the models can't adequately speak to that line. However, from a fisheries perspective, we have to speak to that line. We have a lot of really important fisheries that actually spawn in freshwater and then move out to the marine environment. And without, like, climate change is going to have significant impacts on that area as well. So all I can say is that in progress, and there are many people, one in particular in this room, who has been very, very adamant about making sure that models moving forward resolve those coastal processes. And if they don't, if they're not capable of doing so, that we make it very, very clear in our research and in our presentations that that is a significant limitation.
I agree.
Hello. As the new generation of climate researchers are coming into this mess, what changes would you like to see be made in this field to bring more forward momentum to actually saving the world? What do you want us to do?
You're supposed to talk about hope and new people open. Yeah. One of the things, so I've been around LSU since 2016 and saw a little bit of funding after 2016 go away from climate sciences and now starting to come back. And I've been really, really encouraged with some of the changes we've seen. Skip, we're funded by the climate program office. We've been, seen our budgets increases. What that does is it allows graduates to be funded. I mean, all of three of these folks are funded on Skip. So it enables us to fund students like yourself to do great work in this field. So the more money and more attention to this kits, we can do more to kind of educate and get people interested in the elementary, middle school, high school, hopefully again, college level, in this do great research project, which I know all of you guys do. So I guess that's fine.
So I think what's rapidly happening is the idea of graduate students or even students in general, postdoctoral, even people in their early and mid-career, is that we need to focus that you're no longer just a climate scientist, you're no longer just a marine biologist. A lot of this stuff is a transdisciplinary approach. And so one of the things is that you really have to be willing and to get out there and engage with the other communities and talk with them. At the very beginning, I mentioned, right, just the definition of a word like extreme weather, right? If we went around this room, people would probably have very different definitions of what they would consider extreme. If we went out of this building and talked to the people in Louisiana or Oklahoma or anywhere else, they would have their own definitions. So I think that that's important, and it's incorporating that into our research methods, number one. Number two is, I'm a firm believer that any change or any momentum has to be at a local level by speaking to local people about what matters to them. Okay, so here in Louisiana, there's going to be a lot of focus on maybe wetland preservation or sea level rise or tropical cyclones. Those things are not going to resonate with people in North Dakota. And they're not going to resonate with people, say, New England maybe sea level rise, but there's things there that are not going to resonate with people. And so talking the language, so to speak, of the people locally is how you get them. And I think that is so important to make sure things are made local for them. It's too much of a problem if you come at them and say, the world is going to warm by X degrees Celsius and we have to do something, right? That's too big of a problem. But if it's, we need to preserve the wetlands in the coast of Louisiana, or we need to save this, this national park in Colorado or something, that's something people can grasp, right? They have a tie to, they know, they can see, they've been there. So I would say that those would be the things we would want to do as well.
One quick thing I want to add, just because Cheryl and I spent the entirety of last week at a climate intervention strategies meeting with a whole bunch of climate scientists. We were one of the very few, I think we were actually one of the only ecologists in the room, and the entire workshop we can boil down to one main point, which was the climate community needs impact assessments. They need to understand how climate change is going to be impacting, very speaking to the speaker's last point, is understanding local, regional, what is actually going to happen in the future. We're making these broad global claims that, like you said, have very little relevance for specific areas. So if you would like to get involved in research, I heavily encourage we need impact studies. We need to understand what's going to happen in a changing climate.
from a local and regional perspective.
And you guys actually kind of addressed my question there. I was gonna ask about, your guys' input on the scale. We were talking about synoptic, wave patterns and how that might actually impact somebody who lives in Great Plains is far and few between to the average person. And so I was just kind of curious if you could elaborate on that more. You kind of just did, but maybe also kind of including, even in the more maritime graphs that you had, you still had some differences and more synoptic processes. How can we better communicate that to people on a more local and regional scale? It impacts up in one, but also, trying to, as it was brought up earlier, dumb down the science as well.
So I'll do a couple of things. One is and folks in here too, there's a lot of other folks in here, I know John does a lot of work in West Texas and things like that. When we talk to people in, Oklahoma, when we talk to agricultural people, they see the impacts of drought. They see what's happening year after year, that their farms are losing yield or they're having these severe things, right? That's the part that we have to go at them and target that, but not necessarily, this is my opinion, obviously. Great. My opinion or my approach is not to go at them and be like, this is because of climate change and because we're dumping a bunch of carbon dioxide and we have this, like, that part I think puts people maybe a little bit more on the defensive, and it doesn't open them up to, these are the solutions that we can look at. Here's what's happening, here's where we can go forward. And so I think bringing down these large scale patterns and focusing again on what these people are experiencing, I think is the way to connect the two. The second comment I'll make is, and I'm not personally making it, but when you say something like dumb down the science, that's the term that we absolutely do not want to use, right? But it's a case of, people are hungry to understand. And they might not know all the fancy equations or how these models go in, or, can't maybe read the paper to be right, but they want to know, because again, they see it, they see it. So many people, have lived in a certain area for hundreds of years, right? Their families, whatever else, right? They've seen what's happened. And so they have a hunger to understand. So again, if you can tap into that, I think that is the key. What you don't want to do is, and I think that this is something that scientists are learning over time, is this is not a process where I'm the expert and I know everything, and I'm going to come to your community and tell you what's going on and tell you how to fix it, because I'm the expert and I know everything. I think that's the wrong approach. Okay, and so I think coming at it from, and a lot of it has to do with empathy, but also just a lot of coming at it understanding, asking questions. This one we can learn from them as much as they can learn from us. So keep that in mind, I think.
All right. So we'll go to John. There's a microphone, I think, Vito.
Yeah, well, thank you, folks, very much for the presentations. A larger question that, and this is something that Victor and I are going to be doing as part of our talk later. We often think about climate impacts. We pick the large mega cities to look at the impact, New Orleans, Houston, and whatnot. But if you look at Texas and Oklahoma, Louisiana, the same way, a lot of the population is still in these small towns to medium-sized cities. But how do we address those extreme weather events that correspond to those types of populations? And what are the consequences to them versus living outside of Houston or living outside of New Orleans? What do we know about those impacts going forward?
Well, one of the things that we learned specifically regarding extreme rainfall, we did a small and medium-sized utilities workshop. And what we learned in that was that a lot of the smaller utilities with maybe 2 or 3, 4 people, in small towns, they kind of follow the lead of the bigger utilities. So as soon as water was doing something, a couple of years later, their water utility try to adapt to the same sort of thing. So initially we started targeting those larger utilities and I hope that it would trickle down and they would reach them. But now what we're seeing is that as we expand and reach there's more of these teams popping up, and people like myself and others can now get integrated, stakeholder driven, and visit these communities and talk to maybe a planner or a town, someone in the town council or something,
And they put us in contact with some of the groups that need help, that don't have the capacity to do it. So I think just the growing of this program is helping reach those small local municipalities. It's sort of a shift in just starting big guys over here from down. Now we're sort of trying to get connected.
All right, Jill?
All right, so hi everyone, my name is Jill. I just wanted to weirdly plug my own presentation this afternoon, which is not something I would typically do, but the last session of the day is an interactive session on marketing your site. And the entire thing is an hour-long mind on I promise, it's like 30 minutes, but then we'll have a discussion on everything that Jason was just talking about, this idea of how do you actually communicate to different groups of humans the same type of information to solve these problems. And so hopefully I can speak to a little bit more of that. So if you were gonna
Any other?
Jason, I wanted to ask you about your research on Jetstream. Something it just seems a little counterintuitive to me when we're dealing with how meridional the flow is. Under warming conditions, it's going to become more meridional. And that just seems counterintuitive in that there's less need of a stirring or mixing of the atmosphere. I understand the steering is probably a little more diffused. But can you just talk to that a little bit? Because that just doesn't seem to make a whole lot of sense to me. But I've seen this over and over again. And it clearly is the case.
Yeah, so I think it's the idea more, I think for when we say the jet stream becomes more meridional, then probably the other way to say it would be less zonally strong. So you can produce these undulations that will occur. But there's less the total wind speed or wind shear. If you were to decrease the north-south temperature difference, could go down, right? I mean, that's just mathematically that should happen, right? You don't need this much fear, right? That just sort of leaves you there fear and temperature difference. In terms of what you're saying, I think that's right. And so the idea here is it is hard to wrap your head around, but what we do see, and it's only in preferential spaces that I did say that too, that we are seeing some trends in blocking patterns in certain areas. So I mentioned parts of like Alaska. There's also parts of Central Asia that are also key. So it's not just like everywhere across the globe is going to start being it seems to be preferential type of areas where these elements are going down more, and you're getting more regional transport versus others. I would also say that I'm also sort of convinced. Well, maybe this sort of accept this might be what we would consider like a. In other words, we like my point on I think we're seeing response when the gas stream is evolving, because with time, all of the climate models are pretty in agreement that the gas stream will push forward. And so the mean position will be further to the north, meaning the strong tracks will be much further north than they are today. So I think what we're seeing now is sort of this transition period. And they have to do with some other data processes that are going on currently that start interacting. But it's a trend that we are seeing, and I didn't show it, but temperature trends for the winter months since 1990 across the United States have actually been neutral. There's been a high variance, but it's been almost neutral with time over that 30-40-year period. Again, am I saying in 2100 we're going to have colder winters? No, I'm not, because the heat's going to go up. But this period is interesting, and we're seeing we're seeing that. One more thing I'll quickly mention is how we talked about it, but one thing is that I didn't talk about it, but actually the gas stream during the winter months especially is also tied to variations higher up in the stratosphere. The things in the world, the polar vortex will be going incredible. That has been on the weekly track as well. And so there is a connection there dynamically between the two. So it's not just stratospheric processes that are on the gas stream during the winter, it's also issues that are happening in the stratosphere. So, and I can talk more.
Hi, so my name is Ace. I'm here representing Mr. Indigenous Study. So probably gonna guess where I'm going with this one. Based on all the questions that we've kind of gone over here today, I've been here the whole time, but I've heard a few questions that really kind of came out to me. But based on land use, climate change, adaptation, and all these other issues that we got going on, how do you plan on implementing tribes?
Is that a question for all of us?
Yes.
Great question. So I think there's a couple things. One is, last year I actually did reach out to they reached out to me. There's and it's ITEC, and I'm going back to the acronym saying Intertribal Environmental Council, I think, that's the one. But I did go speak to them about some of the stuff that I was talking about. So I think some of that outreach, working with the CASC, I think would be important. That's how I get connected to them. But the second thing that wraps around all of this is within our field, this is why we have to really encourage and start getting more diverse populations, tribal nations. There's, we talked about, the cities as well, the communities, people of color in those communities are being disproportionately affected by climate change. And this is why it's really important. So, I think I have a definitive answer, but what I will say is, I know me personally, I really want to have the outreach, so I lean on folks at the CASC and other people to help me get connected to that.
I'll just mention that we've done some work out at LSU, actually, Dr. Christine Womack did some work with the tribe. I think they were doing workshops here. And I believe, started at the CASC that was doing that, right? And Skip and I, we've been working with April Taylor on she's at the CASC, doing a lot of tribal work. So we're, and again, I'm just one person, and Skip, we have a whole team. We have members of our team that are specifically working with tribes and with the homeland, doing workshops, and bringing to the table for conversation in specific cities that are also informed. But there's a lot of work at Skip going on, and there's other themes on some of the folks in our organization that relate to that are speaking about. I know it's going on in Skip.
I think it was probably fairly obvious from our presentation, but we currently in the geoengineering world, we have a scale problem. We are operating under a very global perspective that we are actively trying to move further down. We're trying to get to regional, and from regional, we're trying to get to local. We have a very invested interest in working with local and community stakeholders, which is why I'm kind of leaning on the U.S. National Marine Sanctuary system and their community partners and their engagement and their stakeholders to help me then identify and get down to the local scale. We're very actively trying to maneuver our research into a space that's accessible and digestible for local community stakeholders. So I'll just say it's in progress. It's in our brain, and we're trying to figure out the best way forward in order to do that, because we are coming from such a global perspective, and it's really challenging to get it down into the local scale, but we're trying.
Back to my comment, I think for all of us, it's really important to engage in diverse collaboration. And I think one way we can do that as academics is to engage with tribal colleges. If there are workers there, community partners in research proposals, in actually doing the science, doing the impact studies. So I just want to encourage everyone here to make an effort to do that kind of outreach and engagement, not just with Native Americans, but also into our HBCUs. We have a lot of people who are not here at the table with us who should be invited.
I have a quick question for our panelists as well. So I've had some informal conversations with a few of you. The words climate anxiety keep coming up over and over again. So I'm curious, from y'all's perspective, with climate anxiety becoming more and more common as we start to experience the losses associated with climate change, which several of you talked about, what messages of hope would you give to those of us who are experiencing those feelings today?
Messages of hope. Sorry. I'm full disclosure. I'm very new to the geoengineering world. So again, my research is as a marine ecologist, and geoengineering is something that I'm only recently starting to wrap my brain around. But I think what's really, a lot of it is kind of doomsday scenarios, but I think what's really cool about it is that we are trying to develop these tools and technologies, and there are already pathways being developed to make these a reality. That we have incredibly smart people on this planet. We have engineering capabilities, we have technological capabilities that are only increasing and are only becoming more complex and So I think what's aside from the, you know, horrible catastrophic consequences that we're potentially dealing with, is that we have people on board and there are brains already thinking about this and already trying to plan for 10 years out, 20 years out. And we do potentially have the technology to help us get our temperature targets back down. And we still have so many unknowns, so many uncertainties about that. But I think for me, it was really cool to discover that this is in the pipeline. Like it exists. We're already preparing for kind of worst case scenario. So I think for me, the message of hope there is that, you know, we're not alone. Like there's a massive community here that, you know, it's kind of all hands on deck right now, trying to get this climate crisis solved. What's missing here is politicians and the people that can actually maneuver the money in the way that we need it maneuvered. But we do have some incredibly intelligent people that are on this and are trying to, you know, implement and trying to discover what these implementation strategies can get us to in the long run.
Yeah, just like to mention that I think that the last decade, the models have gotten so much better, and we're getting such a good picture of what might happen in the future. And one thing I see quite often is people sort of hone in or focus on this worst case scenario. They look at maps, so you know, RCP 845, 2100, and I think it's important to realize that these are scenarios with you know, likelihoods sort of attached to them, and the probability of, you know, the worst case scenario, RCP 845, you realize is relatively low, it's up or down. So maybe it's not the best thing to focus on, you know, the worst case scenario. And another thing is that, I mean, once this, it's kind of like a snowball going down the hill. Once we've been gaining momentum with more funding coming in, we're gaining momentum, we're seeing advances happen. You know, it's almost like every day I read a paper, it's just like, wow, they didn't understand this, and they're improving. So I think, you know, snowball is going down the hill, we're getting more people involved, need action, we're interested, need a change, we'll see the world. So I'm very hopeful, and I think we're going to have it. Well, 15 years ago, I was a TA, I was at Georgia Tech, where I was at grad school, and we had a survey of weather climate cores, and we asked the students, how many of you accept climate change is real? And there was probably out of about 120 students, probably about 10 or 15 raised their hand out of that. 7 years ago, when I started at OU, I'm teaching one of our climate courses. One of the students wrote in student evaluation, why do we even study climate here? This is weather. This is a weather school, not a climate school. Today, a lot of our applicants that now apply at OU and elsewhere now want to study climate change. They want to look at the impacts of climate change on different areas, whether it be severe weather or energy. The momentum is shifting in terms of that in the student population. Is shifting tremendously over 15 years. The second thing I will say is that things aren't as learning about things helps to bring insight to them. And it probably and a perfect example is what we just went through over the last couple of years with the COVID pandemic, right? Very beginning when nothing was probably some of the scariest times we've ever lived. With time, we've learned a lot more about it. We've learned ways to mitigate, we've learned all those things, right? And so I'm not trying to diminish it, but just say that, you know, those things help. So I think learning and understanding more about climate change can also help to reduce some of that anxiety and actually turn on some hope. Yes, there are things that we can do to actually work for this. So, yes.
Quickly jump in. Phil, beginning your question, you know, what do you want us to do? You ask that question. And the most simple one, you know, in that context of hope and visualization of local to global. The advice I have to you is both. You have to go on board. You have to participate. And we just went through, you know, 2 days ago, most of the most critical event that we might have in the next 10 years. So we have to get involved in that very quickly. And you can do it right away because that propagates. I work internationally, have a lot of work, work in Latin America and Africa. And what happens in the United States is crucial for the rest of the globe. So you can actually have a local effect propagating to the globe. And I can tell you, the transdisciplinary component is fundamental. Doesn't matter if you only do ecology, you have to start getting into the social and economic aspects of it. To round out that education, you can dialogue and come to first. I have been learning a lot about sociology and economics looking at. I'm a wetland ecologist and I'm chemistry. But if I don't have the discourse in order to engage people in not in the United States, but also in other countries, it's very difficult to do that. So we require constant education. It is not terminal. We keep learning all the time and get heavily involved in the social economic dynamics of your community, but also in terms of what you select in your own professional practice. So it's a lot to do. It's you can see now, and I'm glad you asked that question. The first one is be responsible in the sense of where you want to, not asking the question, does climate change exist? It's about, it is there now, we passed that question, it's how do I engage? So, voting, talk to your friends, talk to your family, how to do it. Otherwise, without democracy, it's very difficult to advance this.
One last comment, and then we'll go to break.
Right.
Yeah, it is just a comment. It's not a question, actually. I didn't want to follow up. I gave a talk last week at a petrochemical. I was an invited speaker, which was kind of a surprise. And they were actually on board with some of the things I was saying about climate change, which was shocking. I mean, had I given that same talk 10 years ago, I think I would have been heckled out of the room. But they were actually listening, and I got some great comments and feedback, and they were very open to what I had to say. So that's encouraging to see things like that. The thing I find discouraging, and I don't mean to end on a sour note here, but I work with a sociologist quite a bit up at the University of New Hampshire named Larry Hamilton, and he's had a big effect on one of my PhD students, Win Shao at the University of Alabama. And they've done a lot of work on perceptions of climate change. And what we keep finding over and over and over again, and it's kind of sad, but political party tells you everything you need to know about where people stand on climate change. So I would say we're still a very highly divided country on people who accept it and are skeptical. And so anyway, but things do seem to be changing a little bit. I am somewhat encouraged. So I'll end on that.